Picture a blackboard in a hotel in the Pocono Mountains. It is springtime, 1948. My hands are covered in chalk dust. I am 30 years old, and sitting in front of me, watching me draw what looked like cartoon doodles on this blackboard, are some of the most fearsome minds in the history of physics. Niels Bohr is there. Robert Oppenheimer is there. Hans Bethe is there. Eugene Wigner. Edward Teller. Paul Dirac himself, sitting in the second row, completely silent. And I am drawing little wiggly lines, and little arrows and little dots, and saying these silly cartoons will solve a problem that has had every theoretical physicist on Earth tearing their hair out for 20 years. Bohr stands up. He marches to the blackboard. He looks like he is going to throttle me. It does not go well. I want to tell you that story, not because the story is flattering to me, because it isn't. I made a fool of myself that day, but the cartoons survived. The cartoons spread. The cartoons got smuggled out of that conference by a young kid from England, and within a year, every theoretical physicist who could draw a stick figure was using them. Within 15 years, they had won the Nobel Prize. And today, every physics graduate student on Earth learns to draw them in their first year of school. They are called Feynman diagrams, and they are perhaps the strangest piece of mathematics ever invented, because they don't look like mathematics at all. They look like cartoons. So let me show you how a man got booed off a blackboard, and how the very thing he was booed for became the language of modern physics. To understand why these little drawings mattered, you have to understand what the world of physics felt like in 1947. 1947 was, in some ways, the worst year in the history of theoretical physics. Worse than 1900, when nobody knew what an atom was. Worse than 1925, before quantum mechanics was figured out. Because in 1947, we thought we understood the rules. We had Maxwell's electromagnetism. We had Einstein's relativity. We had quantum mechanics, all sewn up beautifully by Heisenberg and Schrödinger and Dirac in the 1920s. And we had stitched them together into a thing called quantum electrodynamics, which we shortened to KED, and it was supposed to describe how light and matter interact at the most fundamental level. Every chemical reaction, every flash of lightning, every photograph ever taken, every glance you have ever made at another person, photons bouncing off their face into your eye, that's KED. We had the theory. The equations were sitting on the page. Beautiful equations. Compact. Elegant. Gorgeous. And there was just one tiny problem. When you tried to actually calculate anything with them, you got infinity. Not large numbers. Infinity. The mass of the electron? Infinite. The charge of the electron? Infinite. The energy of an atom? Infinite. Try to compute how much an electron deflects when a photon hits it, and the formula gives you a number that grows without bound and never settles down. The theory was telling us, in the most precise mathematical language we have, that an electron weighs infinitely much. And of course, an electron does not weigh infinitely much. An electron weighs about 9.1 times 10 to the minus 31 kilograms. We can measure it. We have measured it. The number is finite. Small, but finite. The theory was lying. This is what I mean when I say the field was tearing its hair out. Imagine you had spent 5 years building a stew. You went out and got the best cuts of meat, the freshest vegetables, the cleanest water. You followed the recipe perfectly, every step. And then you tasted the stew, and it tasted exactly like nothing. No flavor. No salt, no nothing, and you cannot find the mistake, because the recipe is correct, the ingredients are correct, the heat is correct. The stew should be delicious. The stew is bland. Some of the older men, the ones who had built the theory in the 1920s and 30s, started to despair. Wolfgang Pauli, who had a tongue like a razor blade, said that physics had reached an impasse and we needed entirely new ideas. Heisenberg suggested perhaps space and time themselves needed to be modified at very small distances. Dirac, who had given us the equation that started the whole mess, said openly that he believed the theory in its current form was wrong. Wrong. Not incomplete. Wrong. And remember, this is Dirac, the man who could derive antimatter from a piece of paper. If Dirac says the theory is wrong, the theory is in serious trouble. So that was the world I walked into. I had just come back from Los Alamos. I had spent the war doing calculations for the bomb. My first wife, Arline, had died of tuberculosis in 1945, 3 weeks before the test at Trinity. I was 27, exhausted, bereaved, and looking for something to do with my mind. A young assistant professorship had been waiting for me at Cornell, courtesy of Hans Bethe, who had been my boss at Los Alamos and who, incidentally, is one of the kindest human beings ever to have lived. I went up to Ithaca. Cold winters. Nice town. And I started to think about the infinity problem. Here I have to back up and tell you about my graduate school days, because the seeds of those Pocono cartoons were planted years before, when I was a kid at Princeton, working with John Wheeler. Wheeler was my thesis advisor. Wheeler was a marvelous man, the kind of man who took ideas seriously even when they sounded crazy, especially when they sounded crazy. And one day when I was 22 years old, I was sitting in his office and he said something that nobody had ever said to me before. He said, suppose the electron does not interact with itself. Suppose every electron only interacts with other electrons. Forget about the field for a moment. Just have particles, talking to particles, across space and time. This sounded ridiculous, because we knew electrons made fields, and the fields had energy, and the energy was real. You could measure it. You could feel the warmth of sunlight, and that warmth was electromagnetic field energy. But Wheeler had a point. The infinities in the theory came from electrons feeling their own fields. An electron sits there making a field around itself, and then it feels its own field, and the closer you let it get to itself, the bigger the field gets, and the bigger the energy, and bingo, infinity. So Wheeler said, what if we just don't let the electron feel itself? What if we say the electron only feels other electrons? And the field is just a kind of accountant, keeping track of who has paid whom. I worked on this idea with Wheeler for 2 years. We called it the absorber theory. It was bizarre. It involved time running both forward and backward. It involved the idea that a particle here, in this room, somehow knows about every other particle in the universe, all the way out to the most distant galaxies. And only when all of those distant particles agree to absorb its signal does the particle here even begin to emit. It is, on the face of it, completely nuts. Did it work? Sort of. It got rid of some infinities. It introduced new ones. But while I was working on it, I had to invent a new way of thinking about quantum mechanics, because the standard way, the way you learn in graduate school, did not handle this kind of theory at all. And what I came up with was something I call the sum over paths. Picture an electron. It sits at point A, and a moment later you find it at point B. In classical physics, in Newton's physics, you ask, what path did it take? And there is one answer. It took whichever path solved the equations of motion. A straight line, a parabola, an orbit, whatever. One path. The path. Done. In quantum mechanics, you ask the same question, and there is no good answer. People say, well, the electron is a wave, the wave spreads out, the wave does its thing, and then you measure and the electron is at point B. That's true, but it's not satisfying. It does not give you an intuitive picture of what is going on between the start and the end. So I said, what if we say something completely different? What if we say the electron takes every possible path from A to B at the same time? Every path, the straight one, the crooked one, the path that goes via the moon, the path that loops around backward in time. Every conceivable trajectory you could ever draw between those 2 points, the electron takes all of them. Each path gets a little number associated with it, a quantum amplitude, a kind of arrow pointing in some direction. You add up all the arrows from all the paths. The arrows mostly cancel each other out, because they point every which way. But some of them line up. The ones that line up are the ones near the classical path, the path you would have predicted from Newton or from the wave equation. Those reinforce each other. The crazy paths cancel, and what's left is the answer. This was a crazy idea. It was also, it turned out, completely equivalent to all the standard formulations of quantum mechanics. Schrödinger's equation, Heisenberg's matrices, my sum over paths, all the same physics, just dressed up differently. I included it in my doctoral thesis in 1942, and most of my professors thought it was a curiosity. Nobody really cared, but I cared, because when I started thinking about the infinity problem at Cornell, in the cold winter of 1947, I had this picture in my head of every particle taking every path. And one night, working at my desk, I started to draw pictures of those paths. Lines crossing, lines splitting, lines going forward and backward in time. And the more I drew, the more I realized each one of these little drawings was actually a piece of the calculation. The drawing was the math. Let me tell you what was happening. When you try to calculate something in KED, what you really do is something called a perturbation series. The idea is you start with a simple, no-interaction picture of the world. Two electrons, sitting there, ignoring each other. That's easy to compute. Then you add a small correction, the simplest interaction, where one photon is exchanged between them. That's a little harder. Then you add another correction, with two photons exchanged. Harder still. Then 3, 4, 5. The series goes on forever, but each term is smaller than the last, because the strength of the electromagnetic interaction is small, about 1 over 137, a famous number called the fine structure constant. So if you compute the first few terms, you get an excellent approximation to the answer. That's the dream anyway. The nightmare is bookkeeping. Each term in the series, when you wrote it out in the standard way, took pages of mathematics. Pages and pages, full of integrals over four-dimensional space-time, full of products of matrices, full of subscripts and superscripts, and complex conjugates, and Lorentz indices. Just to write down the second-order term for two electrons exchanging two photons could take you a whole afternoon, and you would still have made arithmetic mistakes. People had tried to compute these things and gotten lost. Heisenberg had tried. Pauli had tried. They had all gotten tangled up in the algebra and given up. What I noticed sitting at my desk in Ithaca was that every term in the series corresponded to a particular kind of process. Two photons exchanged, that's a process. One electron emits a photon, the other absorbs it, then a second photon goes the other way. You could draw a little picture of that. Two lines for the electrons, two wiggly lines for the photons, four little dots where the photons get emitted and absorbed. And every line, every wiggle, every dot in that picture corresponded to a specific piece of mathematics. The line was a thing called a propagator, which told you how the electron got from here to there. The wiggle was the photon's propagator. The dot was a vertex, where an electron and a photon meet, and that vertex carried a factor of the electron's charge. You multiply all these pieces together, integrate over the positions of the dots, and you have your term in the series. The picture and the math were the same thing. You could draw the picture and read off the math from the picture. Or you could write down the math and draw the picture from the math. Whichever direction you went, the bookkeeping became almost trivial. Anybody who could draw could compute. I cannot tell you how exciting this was. Calculations that had taken weeks now took an afternoon. I sat in my office with paper and pencil and computed the so-called anomalous magnetic moment of the electron, a number that experiment was just starting to be able to measure precisely, and I got an answer in agreement with experiment to better than 1 part in 1,000. I computed a thing called the Lamb shift, an energy difference in hydrogen atoms that Willis Lamb and Robert Rutherford had recently discovered at Columbia, and again the diagrams gave the right answer. I computed Compton's scattering, electron-positron annihilation, photon-photon interactions, and on every front the diagrams worked. But the diagrams had elements in them nobody could quite stomach. Things that made no physical sense. There were lines that went backward in time. Backward. A line representing an electron traveling from later to earlier. What does that mean? An electron going backward through time? Of course, there is no such thing. But Dirac had shown, years before, that if you took the equation of the electron seriously, it predicted the existence of a particle with the opposite charge, the same mass, called the positron. The positron had been discovered in 1932 by Carl Anderson in cosmic ray experiments. And what I noticed was that a positron going forward in time and an electron going backward in time gave you exactly the same mathematics. Same propagator, same vertex, same answer. So in my diagrams, I just allowed time to run both directions and called the backward-running electrons positrons. The cartoons happily contained both matter and antimatter, mingling with no extra rules. There were other oddities. Lines that started from nothing and ended at nothing. Closed loops, where a photon would briefly turn into an electron-positron pair, which would then annihilate back into a photon. These were called virtual particles, because they did not appear as actual measurable entities, only as transient blips in the middle of a calculation. And they were everywhere in the diagrams. Every diagram had little loops. The vacuum in this picture was not empty. The vacuum was a roiling soup of virtual particles popping in and out of existence. I should have been writing all this up. I should have been publishing papers. Instead, I was frankly drawing pictures and not telling anybody. I was talking with Hans Bethe in his office, scribbling on his blackboard, and Bethe was nodding and saying, "Yes, yes, this is good." But I was not writing down the rules. I had never been a writer. I liked to compute. I liked to play with the symbols. The idea of sitting down and writing a paper that explained the rules to other people, this struck me as boring. In the spring of 1948, Robert Oppenheimer organized a conference at Pocono Manor, a hotel in the mountains of Pennsylvania. This was a sequel to a smaller conference the year before, on Shelter Island, where the Lamb shift had first been announced, and where the field had collectively decided that KED needed a complete reworking. Pocono was supposed to be where the new ideas got presented. About 28 people were invited, the titans of the field, and 2 young men were the main attractions. A fellow my age from Harvard named Julian Schwinger, who had been working out the same kind of corrections in his own way, and me. Schwinger went first. He spoke for almost an entire day, 5 hours, 6 hours, with a single break for lunch. Schwinger had developed a beautiful, mathematically watertight, exquisitely formal version of the corrected theory. He used a technique called canonical quantization. He made everything manifestly relativistic. He computed the anomalous moment of the electron, the Lamb shift, all of it, and the answers agreed with experiment. And his presentation was a tour de force, a literal tour de force. He spoke without notes. He filled the blackboard with mathematics. The audience mostly sat there reverent. When he finished, Pauli stood up and called it the most beautiful thing he had ever seen. Then it was my turn. I got up. I walked to the blackboard. I started to draw cartoons, lines and wiggles and dots. I tried to explain what they meant. I tried to explain that this little squiggle here was a photon. This straight line here was an electron. This loop here was a virtual electron-positron pair. And the audience, who had just spent 6 hours absorbing Schwinger's high formalism, looked at me as if I had walked into the Vatican and started juggling. Bohr objected first. Bohr did not believe in trajectories for electrons. The whole revolution of quantum mechanics, Bohr's revolution, had been about getting rid of the idea that a quantum particle has a definite path. And here I was, drawing electrons, going from one place to another along definite lines, with little arrows. To Bohr, this looked like a return to 19th century physics. He stood up. He marched to the blackboard. He gave me a long lecture, in his soft, mumbling voice, about the uncertainty principle. He told me my pictures were wrong. He told me I had to throw them out. I tried to explain that the lines were not real trajectories. They were terms in an integral. They were not pictures of what actually happens. They were pictures of pieces of a calculation. I tried. I really tried. But I was bad at this. I was bad at speaking the language those men spoke. I argued with Dirac. Dirac said, "Your formula has a term in it that goes like the square of a quantum amplitude divided by another quantum amplitude." He said, "This expression is not unitary." I said, "But I get the right answer." And Dirac, who was a man of very few words, just blinked at me and went silent. The whole talk was a disaster. I left feeling humiliated. I had not convinced them. I had not even, in many cases, made them understand what I was trying to say. In fairness, the men in that room had reason to be suspicious. Schwinger's approach was airtight. Every step was justified by an axiom. Every operator was Hermitian. Every commutator was correct. Schwinger was building cathedrals. I was sketching on the back of a napkin. They could not see, just looking at the cartoons, that the napkin sketches contained the same physics as the cathedrals. I want to be careful here, because Julian Schwinger was a remarkable physicist. We did not get along all that well, but I respected him enormously. Schwinger was the kid prodigy of American physics, a Manhattan boy who had published his first paper at 15, finished his doctorate at 21, and at 30 had already independently solved problems that took entire teams elsewhere. He was a better mathematician than I was. He was more disciplined than I was, and his version of the corrected KED was, mathematically, every bit as valid as mine. What Schwinger had done, and what Tomonaga in Japan had done, both independently, was to take the existing formulation of KED and rework it so that the infinities, while still present, could be cleanly absorbed into a redefinition of just two parameters, the mass of the electron and its charge. The technique came to be called renormalization. The rough idea is that the bare electron, the electron stripped of its surrounding cloud of virtual particles, may indeed have an infinite mass and an infinite charge. But what we measure in experiments is never the bare electron. We always measure the electron together with its cloud. And when you do the bookkeeping carefully, the infinity in the bare mass and the infinity in the cloud's contribution cancel each other, leaving a finite, measurable mass. Same for charge. Two infinities subtract to give a finite number. It sounds suspicious, but it works, and it gives answers that agree with experiment to better than 10 decimal places. Schwinger had done this. Tomonaga, working in Tokyo, in a Japan still in ruins from the war, eating 1 bowl of rice a day, had also done this, 2 years earlier in fact. But his papers were in Japanese and the Western world did not learn of them until later. Both men had achieved the goal, a finite, calculable, predictive quantum theory of electrodynamics. So had I. We had all gotten to the same place. We had taken 3 different roads. They were the highways. I was the goat path through the woods. The question, after Pocono, was whether anybody would ever realize the goat path led to the same destination. Enter Freeman Dyson. Freeman Dyson at this time was 24 years old. He had come over from England to study at Cornell. He was a mathematician, really, more than a physicist, with a sharp, hungry mind, and he had the great good fortune to find himself sharing an office with me during the months I was developing my diagram method. He watched me, curiously, day after day, scribbling these little drawings, refusing to write papers, occasionally muttering to myself. He came to Pocono. He saw Schwinger. He saw me. He saw the room reject my approach and embrace Schwinger's. And he came away with a question that nobody else seemed to be asking. What if both men were right? Dyson decided to find out. In the summer of 1948, Dyson took a Greyhound bus across the United States, from New York to California. 48 hours on a bus. No sleep. He sat in the back of the bus, watching cornfields go by, and he thought about Schwinger and Tomonaga and Feynman. And as he later wrote, somewhere around Nebraska he had a vision, a clear vision, of how the 3 approaches fit together. They were not 3 different theories. They were 3 different views of the same theory. Schwinger and Tomonaga were doing the formal mathematical legwork, I was doing the computational shortcut. The connection between them was a particular set of operations called time ordering. And once you saw that, the equivalence was obvious. He arrived in California, sat down, and over the next few months wrote 2 papers. The first was called The Radiation Theories of Tomonaga, Schwinger, and Feynman. The second was about something called the scattering matrix in quantum electrodynamics. Together those papers did 3 things. They proved that the 3 approaches were mathematically equivalent. They derived the rules for my diagrams from first principles, so they were no longer my private hieroglyphics. They were a public technique anyone could learn. And, most importantly, they wrote it all up in clear, beautiful, accessible English, with explicit instructions like a cookbook. Step 1. Draw all the diagrams. Step 2. Attach this factor to each line. Step 3. Attach this factor to each vertex. Step 4. Integrate. Dyson's papers were sent around in preprint form in the fall of 1948, before they were even published. And within months, every theoretical physicist on the planet was drawing the cartoons. Bohr came around. Oppenheimer, who had openly disliked my talk at Pocono, sent a kind of telegram of apology, basically. Dirac characteristically said little, but eventually conceded that the diagrams gave correct answers, even if he never quite forgave them for not being unitary in the way he wanted. I have always said that Dyson saved the diagrams. I would have published eventually, but it would have taken me years, and they might have been ignored. Dyson made them respectable. Dyson made them teachable. Dyson made them part of the curriculum. Whenever I am tempted to take credit for the diagrams, which is often because I am that kind of person, I have to remind myself that without that boy on a bus across America, the cartoons might have died on a blackboard in the Poconos. I want to slow down and tell you exactly what these cartoons are, because I have called them cartoons. And that's a fair description, but it gives the wrong impression. They are not illustrations. They are not pictures of physical events. They are something stranger and more useful than that. Imagine you are computing the probability that an electron coming in from the left will scatter off another electron coming in from the right, and the two electrons will leave going in some particular directions. This is one of the basic problems in KED. Now you cannot, in quantum mechanics, just say one thing happens. The two electrons might have exchanged one photon, or two photons, or three, or one of the electrons might have briefly emitted a photon and reabsorbed it before any exchange happened. Or the photon might have, in flight, briefly turned into an electron-positron pair and then turned back into a photon. Or all of these things at once. Quantum mechanics does not let you choose. You have to consider every possible way the process could happen and add up the contributions, with each contribution weighted by its quantum amplitude. A diagram is one way the process could happen. The simplest diagram, the lowest order one, has just two electron lines coming in, exchanging one photon and going out. That diagram contributes one piece to the answer. Then you have to draw all the diagrams with two photons exchanged. There are several of those. Each one contributes another piece. Then you have to draw all the diagrams with three photons. And so on, forever, in principle. In practice, you stop after the first few orders, because the higher order pieces get smaller and smaller by factors of the fine structure constant. To extract the actual numerical contribution from any one diagram, you follow a recipe. Each electron line is replaced by a specific mathematical expression called the electron propagator, which describes how an electron moves between 2 points. Each photon line is replaced by the photon propagator. Each vertex, where an electron line meets a photon line, contributes a factor involving the electron's charge and a thing called a gamma matrix. You multiply all these factors together. Then you integrate over the positions of the vertices. The integral is over four-dimensional space-time, all of it, every possible location where the photon could have been emitted, every possible location where it could have been absorbed. And what comes out of this integral is a number, complex in general, which is the contribution of that one diagram to the total amplitude. You do this for every diagram. You add up the contributions. You square the magnitude of the sum. And that gives you a probability. That probability is what you compare to experiment. What the diagrams do is automate the bookkeeping. Without diagrams, you would have to keep track of which electron emitted which photon at which time, and make sure you have considered all possible orderings and not double counted, and gotten the signs right, and applied all the relativistic corrections in the proper places. With diagrams, you draw a picture. The picture tells you exactly what to write down. You cannot get lost in the diagram. because the diagram is a topological object. Lines connect to vertices. Vertices connect to lines. There are only certain ways to connect them. So the rules are simple. Apprentices can do it. Computers can do it. By the 1960s, calculations that would have been beyond the reach of the best minds in 1940 had become homework problems for graduate students. Let me give you a concrete example so you can feel the technique. Take an electron sitting in a magnetic field. The electron has a magnetic moment. It acts like a tiny bar magnet. From the Dirac equation, the original equation written down in 1928, you can predict the strength of that magnetic moment exactly. The prediction has a particular value. We call it the Dirac value, or the G factor of 2. Now experiment, when the experiments got good enough by the late 1940s, started to reveal that the actual measured magnetic moment was not exactly the Dirac value. It was a little bigger, not by much, about 1 part in 1,000 bigger. This was the so-called anomaly, the anomalous magnetic moment of the electron. Where does the extra bit come from? In the diagram language, you say, the simplest diagram for an electron interacting with the magnetic field is a single electron line with a single photon coming in from outside, where the photon represents the magnetic field. That diagram gives you the Dirac value, the boring G factor of 2. But there are correction diagrams. The next simplest one has the electron emit a photon, then absorb the magnetic field photon, then reabsorb its own emitted photon. A loop, a virtual photon, briefly carried alongside the electron, modifies the way the electron sees the magnetic field. Compute that diagram, and you get an extra contribution to the magnetic moment. The number that comes out is the fine structure constant divided by 2 pi, which is about 1 part in 860. Schwinger computed this in 1948. He got the right answer. Tomonaga's group also got it. So did I. We all agreed. The first correction to the magnetic moment from one virtual photon was the fine structure constant divided by twice pi. Then people started computing the next correction with 2 virtual photons in 7 different diagrams. That took about a year of work. Then the next, with 3 virtual photons with 72 diagrams. That took most of the 1950s. By the time we got to 4 virtual photons, with about 900 diagrams, computers had to be brought in. By 5 photons, with over 12,000 diagrams, the calculation was a multi-year, multi-person project. And every step of the way, the experimental measurements got more precise too. The theory and the experiment have been chasing each other up the precision ladder for decades. They agree, today, to better than 10 decimal places. There is, as far as I know, no other prediction in physics that is so well tested by so many people over so long a time, with so much agreement. There is something about the diagrams that troubles even me sometimes, even now. The diagrams have, baked into them, the idea of virtual particles. Particles that are not real. Particles that exist only inside the diagram, only as intermediate steps in a calculation. Particles that violate the usual relationships between energy and momentum and mass that we expect of real particles. A virtual photon can have 0 energy and non-zero momentum, which a real photon cannot. A virtual electron can be off-shell, meaning its energy and momentum do not satisfy the usual relativistic energy-momentum relation. These are not physical particles. They are mathematical entities. They cannot be detected. They cannot be isolated. If you tried to put a detector inside a diagram, the diagram would change, and the virtual particles would not be there anymore. So when somebody tells you that the vacuum is full of virtual particles popping in and out of existence, that is true in a certain sense, but it is also misleading. There are no little ghost particles flickering on and off in the empty space inside this room. What there is a set of calculations we do, in which our most successful theory of how particles interact gives us numerical answers that match experiment, and the way we compute those answers involves drawing pictures with intermediate lines that look like particles. The pictures are real. The pictures work. Whether the virtual particles in the pictures are real, in any deep sense, depends on what you mean by real, and physicists have been arguing about that for decades and have not settled it. I want to be honest about this. I do not know whether virtual particles are real. I think they are useful fictions, and I am suspicious of useful fictions sometimes feeling more real than they ought to. Other physicists, very smart ones, will tell you the virtual particles are absolutely real. The vacuum really is foaming. The diagrams really are pictures of what happens. We do not know. The mathematics works. That much I am sure of. There is one more piece I have to mention, because I cannot end the story honestly without it, and that is the matter of renormalization. The infinities did not go away when we drew the diagrams. The infinities were still there. If you tried to compute, for example, the diagram where a single electron emits a photon and reabsorbs it, a kind of self-interaction, the integral over the photon's possible momenta blew up. You got infinity again. What we learned to do, what Schwinger and Tomonaga and Bethe and I and others worked out together over those years, was to handle the infinities by a kind of redefinition. You say, the mass of the electron that appears in the original equation is not the mass we measure in the laboratory. The mass we measure in the laboratory is the bare mass, plus the contribution from all the self-interactions, the cloud of virtual photons surrounding the electron. The cloud has infinite contribution. The bare mass is also infinite, in the opposite direction. We never measure either one separately. We only measure the sum. So we redefine, take the bare mass to be whatever it has to be, so that the sum equals the measured mass. Same for the charge. Then, when you compute any other physical process, you use the measured mass and the measured charge, and the answers come out finite. This procedure horrified Dirac. It horrifies certain mathematical purists today. It is, on the face of it, a sleight of hand. You start with a theory that gives infinity, you subtract one infinity from another, and you call what is left the answer. How can that possibly be right? I will tell you the most honest thing I can say. I do not know. I have never known, in all the years I worked on KED, exactly why renormalization works. I suspect it works because there is a deeper structure underneath, something we have not yet seen, of which our current theory is only a low-energy approximation, and the infinities are signals that we have pushed our approximation past the point where it makes sense. But that is a guess. What I can tell you is that the procedure gives correct answers. The anomalous magnetic moment of the electron, computed from KED with renormalization and Feynman diagrams, agrees with experiment to better than 10 decimal places. That is the equivalent of measuring the distance between New York and Los Angeles to within the width of a human hair. No theory in the history of science has ever been more precisely tested. So whatever is going on with renormalization, whether it is mathematical magic or pointing to something we have not understood, the answers are right. I once said in a lecture that KED, our theory of light and matter, is in my opinion the best theory we have. I still think that. I think it is the most accurate, the most predictive, the most thoroughly tested theory in physics. And the cartoons are at the heart of it. The Nobel Prize came in 1965. It was shared, 3 ways, between Tomonaga, Schwinger, and me. I was in Geneva at the time, traveling. The phone rang at 3 in the morning. Some reporter from the press woke me up to tell me I had won. I think my first response was to ask if I really had to take it. I do not say this to seem humble. I say it because by 1965, the diagrams had been part of physics for almost 20 years. They were no longer mine. Every graduate student drew them. Every textbook contained them. The work that had won the prize had stopped feeling like my work and started feeling like furniture, like the walls of the discipline. The prize was a strange feeling. Pleasant, but strange, as if someone were giving you an award for inventing the alphabet. I went to Stockholm. I gave the Nobel lecture. I told the story of how the diagrams came to be. I tried to be honest about the fumbling, about the false starts, about the parts where I had no idea what I was doing. I think people sometimes assume that scientific discovery is a clean march from confusion to clarity, and it is not. It is much more like cooking dinner with the lights off. You bump into things. You drop things. You taste things, and they are bad. Eventually you arrive, somehow, at something edible, and then later you write up the recipe and pretend you had it all in your head from the beginning. The diagrams have spread far beyond KED in the years since. Particle physicists draw them for every interaction known to nature: electroweak processes, strong force interactions, the quantum chromodynamics of quarks and gluons. The standard model of particle physics, which describes essentially everything we know about subatomic matter, is a giant calculation, built diagram by diagram. Even outside particle physics, condensed matter physicists draw analogous diagrams for electrons in metals, for phonons in crystals, for the strange collective behaviors of superfluids and superconductors. The technique has migrated. The cartoons have colonized the field. What I find most amusing, looking back, is that I was almost talked out of them. After Pocono, I came home, and I genuinely considered abandoning the whole approach. Bohr had said it was wrong. Dirac had said it was inconsistent. Oppenheimer had been chilly. Maybe Schwinger's way was the right way. Maybe I was kidding myself. I remember sitting in my apartment in Ithaca, going through the calculations again and again, looking for the mistake the great men had assured me must be there, and finding nothing. The diagrams kept giving the right answers, and eventually I decided that if the right answers came out, the method must be sound, no matter how strange it looked. That decision, more than anything else, is what saved the diagrams. Not cleverness, stubbornness, the refusal to let people who could not draw tell me my drawings were wrong. There is a lesson in this, I think, for anybody trying to do something new. The people who already know the field, who have spent 30 years building the dominant approach, are not necessarily the right judges of a fresh idea. They have invested too much in the old way. They cannot see the new way without translating it back into the old way, and in the translation, the new way loses its power. If you have a method that works, even if it looks like a cartoon, even if great men tell you it is nonsense, you have to have a kind of faith in your own arithmetic. The arithmetic does not lie. The arithmetic told me every night in Ithaca that the diagrams were correct, and the arithmetic, in the end, was right. The deeper lesson, though, is about the strange relationship between mathematics and reality. The diagrams are not pictures of nature. Nature does not contain little stick figures with arrows. Nature contains, as far as we know, fields, quantum fields, pervading all of space and time, fluctuating, interacting, and somehow producing the particles and forces we observe. The diagrams are a tool we use to extract numerical predictions from those fields, in a particular regime where a particular kind of approximation is valid. They are no more pictures of reality than a recipe is a picture of a meal. And yet, when you draw them, when you stare at them long enough, you start to feel as though you have caught nature in the act of making particles. You start to think the cartoons are real. They are not. They are scaffolding around something deeper, something we still only partly understand. I sometimes wonder what physics will look like in another 50 years. Whether the diagrams will still be the workhorse, or whether something even simpler, even stranger, will have replaced them. Whether somebody, somewhere right now, is sitting at a desk in some cold city, scribbling lines on paper, working out a new way to think about the same old problem, a way so peculiar and so inelegant that the great men of the present moment will laugh at it, and the great men of the future moment will use it without thinking. I hope so. I really do, because that is how progress happens. Not by cathedrals, by cartoons. So if you are out there tonight, drawing your cartoons, scribbling your strange diagrams, calculating your numbers, and getting laughed at by people who think you are not being serious enough, I want you to know something. I have stood in front of a room full of titans who told me my work was wrong. I have left that room feeling like a fool. I have walked home and gone back to the desk and kept drawing, because the arithmetic told me to, because the answers kept coming out right. The cartoons survived. The cartoons spread. The cartoons won the Nobel Prize. And the only reason any of that happened is that I was too stubborn to throw away a piece of paper that worked. So go ahead. Draw your cartoons. Tell me, if you would, what is the strangest tool you have ever used to understand something hard? Some weird picture, some private metaphor, some homemade trick that worked when nothing else did? I would like to hear about it.